general relativity, step by step. I'm going to go through a practical example of these calculations here with this integral. For the Earth, what have we got? The radius of the Earth I've got here is 6.4 times 10 to the 6 meters. The mass of the Earth is 6 times 10 to the 24 kilograms. C is 3 times 10 to the 8 meters per second. G, big gravity, 6.671 times 10 to the minus 11. So let's work out the Schwarzschild radius. 2gm over c squared equals the Schwarzschild radius. Well, let's work it out. We need 2 times 6.671 times 10 to the minus 11 times mass of the Earth. What did I have for that? 6 times 10 to the 24 over c squared. 3e8 squared. That's the radius in meters. So what's that? That's 10 millimeters. That's 10 millimeters or 8.8 millimeters. Okay, well, let's just go back to my. So we've got this. We've got 2m equals 0.01 meters. That's a centimeter. I think Einstein said it was about the size of a peanut or something, which kind of makes sense. Okay, and what I want to do is to work out this distance here from the radius of the Earth, and the outside circle there is the radius of the Earth plus 1 meter. So let's just work out how far. And of course, in classical physics, you would climb 1 meter. But in this non-flat space, it won't be 1 meter. There'll be an extra term because the equation was so complicated. So let's work it out. The radius of the Earth was 6.4 times 10 to the 6. And then we have to divide by 0.01 equals, well, it's going to be 6.4 times 10 to the 8, isn't it? And then if we have 6.4 times 10 to the 6 plus 1, because we're climbing up an extra meter, plus 0.01 of 0.01, well, that's going to be 6.4 times 10 to the 8 plus 100. So when you climb a meter at the Earth's surface, that's climbing 100 Schwarzschild radii. Okay, well, let's try that. Let's see how many Schwarzschild radii it actually is. .4 times 10 to the 8. Bonk. Bonk. Just give it a minute to warm up. Come on. Come on. Just give it a minute. These figures aren't exactly accurate here. All I'm doing is getting an order of magnitude just to show you the level of the effect. I mean, I've taken. I mean, these numbers here are not precisely calculated either. And of course, that should be 8.8 instead of 0.01. But it's enough. Really, what I'm trying to show you is if you climb 100 Schwarzschild radii from sea level, then your local distance is not going to be the same. Your proper distance is not going to be the same. It's not going to be 100. That's if we ever fire this thing up. And I can't even find it. Oh, here it is. Still black. Come on. Quite sure why this is taking so long. Claims it's running, but I don't think it is. Yep, says it's running here. Right, finally switched itself on. And of course, I can't remember what the values are now. 6.4 times 10 to the 8. Right, let's give that a where is it? Here it is. Oh no, it's this one. So I'm just going to replace those. 6.4 times 10 to the power 8 to 6.4 times 10 to the power 8 plus 100. Oh, that's 10 to the power 9. 8 plus 100. So you remember the Schwarzschild radius was 8.8 millimeters, and so we're going to climb up 100 Schwarzschild radii in Schwarzschild radius units and see how far we actually have to climb. Let's have a look at this. 100.0. That's not very edifying, is it? Let me. That's exactly 100, isn't it? I was hoping to show you a tiny deviation. Well, let's 6.4 times 10 to the 8. Let's replace that with something more accurate. 64. So that's moving it 1, 2, 3, 4, 5, 6, 7, 8. 4. It's moving it 1, 2, 3, 4, 5, 6, 7, 8. Let's try that. Oh, of course, it's giving an answer, isn't it? So I'll calculate it like this and see what happens. Point. Aha! There we go. So there's a little difference. So you're climbing up 100 Schwarzschild radii, but that's in terms of the Schwarzschild radial coordinate r. How far do you locally have to travel? How far do you measure it? Well, it's 100.0000000699907 meters, a tiny bit more, which shows rather convincingly that we have recovered flat space far away from the Schwarzschild radius. Of course, the vacuum equations that we solved to get the Schwarzschild solution do not apply in the inside of the Earth. Inside the Earth, you have got a non-zero stress energy tensor, and so you are solving not the vacuum equations, but the full field equations, and they're different. You don't have an 8 millimeter radius Schwarzschild radius thing in the middle of the Earth, which you must avoid or it'll suck you in. Because the equations are different and the vacuum solution doesn't apply. Anyway, I'm going to stop there, and there's a nice little tiny discrepancy between flat space and the Schwarzschild metric right there, 69907. Stop.